All right, this is Math 150, Section 2, lecture round 21, give or take. We're now moving to the final unit of the class, which is sequences and series. So this is a very strong change from what we've been doing before. In some sense, this is the material I think you're going to use the most. So one of the big ideas in calculus in one variable is to take a complicated function and replace it with what? So in calculus, what do we try to, at least locally, we try to replace a complicated function with
a straight line.
A straight line, and that's the notion of the tangent line approximation. In multivariable calculus, instead of the tangent line, we have tangent plane, and you can go higher and higher, you can have the tangent hyperplane. And these do a good job, but not surprisingly, if I were to do a better approximation, I would hopefully be able to do a better job. And the idea is, can I have a more complicated approximation than a straight line? Can I do so in a very quantified way? And it's going to give us these sequences and series. So a sequence is a collection of terms. The series is the sum. And for many things, what we do is we have like the main effect, and then the secondary effect, and then the tertiary effect. And the hope is that as you go further and further down the terms, they have less and less of an impact. And if that's the case, then the sum will converge. And you can get a really good approximation for it by taking only a couple of values. Okay, so the big thing we'll be leading up to, and I'm just trying to give you some sense. We seem to be off by some lights. Okay, so the big thing we're going to be leading up to is Taylor series. And the idea is to try to approximate a complicated function with a sequence of functions that are getting better and better to it. So if I give you some function f of x, the first order approximation is to say, well, if I know its value at 0, and that's all I know, then I'll just say it's f of 0 everywhere. And this would be the 0th order Taylor series. The next thing is, maybe I know the instantaneous rate of change at 0, the first derivative at 0. And then this is our tangent line approximation. And then it's x. It's really x minus 0, but I'll just write it as x. We can then keep going. Maybe I know the second derivative over 2 factorial x squared. And then the third derivative. And the hope is that this series converges, and it converges to the function. And that hopefully these terms are decreasing rapidly, so if we just truncate a bunch of them, we get a really good approximation. So this is expanding a function in terms of a multiple of 1, x squared, x cubed. If you want, when we get to linear algebra, you'll have your different direction vectors. We've seen that for tangent planes. My directions here are 1x, x squared, x cubed. And so on and so on and so on. These are my directions. This is how much in the direction of 1, how much in the direction of x. This is a convenient basis for us to expand things in, but it's not always the best basis to expand things in. And whenever you have an infinite series, the first fear is always, does it converge? So for notation, I will write the sum, n goes from 0 to infinity, of an x to the n to denote my series. So this is just going to be a0 plus a1x plus a2x squared, etc., etc., etc. And here, an, we put the n in parentheses like this to note it's the nth derivative. There are times when it is better to use other bases than 1x squared. So you might have heard of Fourier series, or you might have heard of wavelets. I'm going to give you a quick rough sense as to how images, video images can be streamed. So imagine you have a picture and you want to send the picture. Well, we can put little dots of color at every single place. And then we can just send all the dots. Unfortunately, if you have a lot of resolution and a lot of pixels, and you want really good motion, you're going to have to send an enormous amount of information. So what you want to do, very similar to functions, is I want you to send a few points of the function and then interpolate and try to find a function that goes through it. So if I give you a couple of points, can you give me a graph? Can you give me a function that passes through this? So what we normally do is we split the picture into 3 different pictures. Who remembers their colors? What are the
red, green, and blue.
red, green, and blue. So if I give you the red, green, and blue value of each pixel, I can then combine them and figure out what the color of the pixel should be. So I'm really sending three things. I'm sending a red, I'm sending a green, and I'm sending a blue. I am simplifying things a little bit for the sake of an introduction, but roughly this is what goes on. So now I have a red function, and it gives me my red intensity everywhere. So I will have my function r of xy, my function g of xy, and I'll have my function b of xy. How many of you are watching streaming video on very primitive calculators or wristwatches? Okay. What do you watch video on?
Phone and laptop.
Phone, laptop, maybe a TV. You're watching it on something that has decent processing power. So you can use that. So the more information you transmit, the longer it's going to take, the more chance you have of error. What you want to do is you want to transmit as little information as possible and then have it reconstructed on the other end. So what we want to do is we want to transmit just a couple of key values of this function and then use our processing power on the other end to reconstruct what's going on. So what we're going to do is we expand our xy into a series. It'll be a series in two variables now, x and y. And instead of using 1x, x squared, x cubed, it turns out it's technically easier to use a basis in terms of sines and cosines. They have really nice convergence properties. And you might talk about the harmonics or the frequencies. But this is essentially what's going on. What we're doing here will generalize to allow us to handle something like this. And it'll allow us to exploit the power we have on our end. So I'm just trying to give a motivation as to why we're going to be spending so much time on sequences and series. All right, so let's do an example to illustrate why we need to be careful with what we're doing. So we've seen many times in this class connections between probability and multivariable calculus. One of the most important densities is the Gaussian. F of x is 1 over square root of 2 pi e to the negative x squared over 2. So this is the standard normal, the Gaussian, or the bell curve. And it looks a little bit something like this. Something like that. And here's x equals 0. And so if we want to calculate the probability of events, we need to integrate under this curve. So the cumulative distribution function is the integral from minus infinity to x of f of t dt. So this is the integral from minus infinity to x of 1 over square root of 2 pi e to the negative t squared over 2 dt. The 1 over square root of 2 pi, that's not a problem to deal with. The challenge is, how do we deal with the exponential? We need a function whose antiderivative is e to the negative t squared. There is no elementary function, unfortunately, that has derivative e to the negative t squared over 2. Any thoughts as to how we could try to handle this? Any thoughts on what we could do to the exponential? Bless you. How's the exponential defined? Yeah. What does e of u equal? What's our definition of e to the u?
E to the negative t squared over 2.
Well, that would be what u would be for this particular problem. What is e to the u? I mean, yes.
The derivative of e to the u?
No, that's a property it has. E to the u is its own derivative. But how do we actually compute e to the u? What is e to the u? I know we've done this in this class. There are two different ways you've seen. One is the product formula and compound interest. And then we also had another way. We had the series expansion. This is the sum, n goes from 0 to infinity, of u to the n over n factorial. Right? This is our definition of e to the u. One of the things we're going to show in this series, this part of the course, is that this series converges for every value of u. the n factorial is growing so rapidly that no matter what value of u you take, this converges. So we could substitute that in here. So we have the integral from minus infinity to x. I'll pull out the 1 over square root of 2 pi. And then we'll have a sum, and it goes from 0 to infinity. U is going to be negative t squared over 2 to the n over n factorial dt. So what should we do with the integral sum? What techniques do we have to evaluate this? What would you like to try? Yes?
It looks a little bit like a geometric series.
A little bit.
If you have negative t squared over 2 as a...
Right, the problem is we have the n factorial down
Right.
below. So each term is not the same as the previous by just a scaling factor. If we didn't have the n factorial, we could do that.
I think you can sort of, you can integrate the series.
So switch orders,
Ooh.
right?
Yeah.
Can you integrate t squared without any trouble? Is that a nice function? So switch the orders of integration. So my kids and I watched the Cam bubble wand video again this morning. You wave your magic wand and say, switch sums, switch sums. And when you do this, you get 1 over square root of 2 pi. Now we have the sum outside. Sum n goes from 0 to infinity, 1 over n factorial, integrate from negative infinity to x. And actually, I can pull out the negative 1/2 to the n. So negative 1/2 to the n. I'll have t squared dt. And what do I get when I integrate t squared dt from negative infinity to x? Yes?
t cubed over 3.
T cubed over 3. So this part is t cubed over 3 at negative infinity and x. And what does that equal?
Undefined.
Yeah, you'll get x cubed over 3 minus negative infinity cubed over. So you get it's positive infinity. So we're going to be getting an alternating sum of infinities. So this is a legitimate example of a time I cannot switch orders. And if you put in absolute values, you'll see that the integral of the sum of the absolute value is infinite. This is a place where Fubini's theorem is not applicable. We cannot switch orders. It's a natural thing to try, but unfortunately when we try to switch orders here, we're left with an infinity. In fact, we're left with infinitely many infinities of alternating signs, and somehow it's all going to cancel in a nice way. So the question is, how the hell do you make sense of this integral? How do you approximate this? How do you come up with a series that gives you a good approximation to this value? We need that. This fails miserably. Is there a way to fix this? Is there another approach? So for extra credit, come up with a way to make sense of this series. There are at least 2 different things you can do to lead to a number that will be a terrific approximation to this with just a few terms. And depending on which one you do, it'll be either extremely good or just good. So extra credit for next class, try to figure out how you would approximate that. So I want you to just really have a motivation as to why we're spending so much time on sequences and series. These convergence issues can be extremely delicate. Just because I write something on the board does not mean it will converge. Okay. So the first thing we looked at today and in the video was the basketball game. I'm not going to go into too much detail because it's in the video. I wanted to at least have some people playing the basketball game just to really drive home the point. That what we have here is a memoryless process, and you can use this to evaluate things extremely easily. In some sense, this is almost similar to induction, where you try to reduce to a previous case. You reduce to something that's already known. Mathematicians are lazy. So the way things are working in the basketball problem So I use Bird, and I think I use Magic Johnson. Why do I use Bird and Magic?
They were rivals.
They were rivals, and I'm an old Celtics fan, and I love the Celtics-Lakers rivalry. I had a student a few years ago who rooted for every team I hated. Lakers over my Celtics, Giants over my Patriots, Yankees over my Red Sox. And because he was such a good student, I actually worked into one of my lectures the catch that was it Tyree made on the helmet?
Yeah.
Yes, I worked that into my lecture to be a fair and balanced professor. One of the most painful lectures I ever had to give. Okay? But if you were to probably redo this, Bird and Jordan would be better. If anybody's ever seen those old Super Bowl commercials, but they're Nothing But Net series, or Space Jam. But I'm going to do Bird and Magic from my childhood. So we will assume Bird always gets a basket with probability P. And then there's a lot of different ways of doing it. Sometimes people say Q is the probability that Magic gets a basket. People sometimes like to use Q as 1 minus P, the probability something doesn't happen. So I'm going to do a little bit better notation. I'm going to use P sub B. Why do you think P sub B? Bird. And P sub M for Magic. And so this is the probability that they make a basket, and we will assume that they never tire, and that they always shoot and get a basket with the same probability. And we let X be the probability Bird wins going first. And our first solution is, well, how could Bird win on his first shot? There's only one way. Ball goes in. What's the probability Bird wins on his first shot?
P of B.
P sub B. What's the probability Bird wins on his second shot?
1 minus P sub B times P sub B.
Almost. So this is the probability Bird misses.
Times P sub B.
Well, then that's the probability that Bird gets the shot. Okay, but we're missing something else. After Bird misses, what must happen?
1 minus P sub M.
1 minus P sub M. Magic misses, and then Bird gets it. And it's better to, let's just call that R. That's the probability they both miss. And then the next one would be R squared P sub B. Each one has to miss twice. And then R cubed P sub B. And so on and so on and so on. So this is a really good problem to introduce sequences in series. My sequence is maybe R to the n PB. That's the nth term, or the n plus first term in the sequence. Unless you want to call this the 0th term, it's a little bit annoying. I don't really care. And then we're just adding them all together, so our sequence is being converted to a sum. And so the first question is, does the sum converge? Well, it should, because there should be a probability that Bird wins. And these terms are fortunately decaying fast enough. And so what you notice is that this is a geometric series. I can pull out the P sub B, and it's 1 plus R squared plus r. And so if we knew the geometric series formula, we would now be done. What I want to do is I want to use this as another way of proving the geometric series formula. So I believe earlier in the semester we proved the geometric series formula by just multiplying by R, subtracting, and doing some algebra. Here is the memoryless proof. I find it interesting to say you must remember the memoryless proof, but there's a really good concept going on here. Once Bird shoots and misses, and then Magic shoots and misses, it's as if we just started the game. So this does not often happen in life, where you can say you have completely returned to a previous position. But if you do, then what happens from that point onward is the same as what would have happened from that point onward in the beginning. Will you ever have something like this in tic-tac-toe, where you will ever return to a previous position? No. Can you give me a game where you could have a return to a previous position? Hopefully something other than this exists. Yes? Chess. You can return to the exact same configuration on the board. There are only finitely many configurations on the chessboard, even if you allow pawns to score. And I believe there's a rule in chess, threefold repetition of position. If you get the same position on the board 3 times, I think the game is a draw. Or at least some people play that way. Are there other games where you can return to the same position? Tevis?
Never mind. I was going to say Parcheesi, but then I realized the other players had moved.
I'm trying to think. It's been so long since I played Parcheesi.
It's not, because other players could move around the board, so I don't know positions that they're in.
Well, but they could also return to the same point.
Okay. Well, yeah.
It is possible to get the same positioning in Parcheesi. Backgammon is another one. There's a lot of games where you can return to where you were. And so if X is the probability that Bird wins, he could win on his first shot, or they both miss. And now that they both missed, it's like we're playing the game right now. And the probability that Bird wins is just X. And so now we get 1 minus R times X is PB. So X is PB times 1 over 1 minus R. But X is also PB times 1 plus R squared. And there's the geometric series formula. So there's a proof of the formula for the sum of an infinite series. So sometimes we have closed form solutions. Now, what are our restrictions on R? R is 1 minus PB times 1 minus PM. What are the possible values R could take on? Yes?
From 0 to 1.
From 0 to 1. How could R be 0?
If both of their, or if one of the probabilities.
If one of them is perfect, you could have R equals 0. What's the largest R could be? 1. If R equals 1, what will happen? Yes?
Both of them will miss.
Both of them will miss forever. What should Bird's probability of winning be if they both miss forever? 0. And if you look at 1 over 1 minus R, you get 1 over 0, which is 1. What's 1 over 0? It's undefined. It matters, are you approaching out from a positive or a negative? Well, as we take the limit as these get closer and closer and closer to 0, this is always going to be a small positive number. So this would be 1 over... Oh, but wait. We're multiplying by PB. Things are now getting interesting. So typically 1 over 0, that would be infinite. But we have a 0 over here. We have PB times that. So we have 0 divided by 0. Can we make any claims when we have 0 over 0? No. Good. So the formula at least realizes it should not say anything in the case when R equals 1. So you really want to get into this habit of testing whatever you get. Is this right? Is this reasonable? This is reasonable so long as R is between 0 and strictly less than 1. It turns out you can modify this if R is negative. So this argument, you cannot have this nice geometric interpretation if R is negative, because you're not going to have negative probabilities. So we've only proven the geometric series formula if R is positive. As a nice extra credit exercise, show that if you know the geometric series when R is positive between 0 and 1, you also get it if R is negative between 0 and 1. So knowing it for positive values, you get it for negative values as well. Okay? So what I'm trying to do, this is the last part of the semester, I'm trying to throw in a variety of problems, a few more challenging than the ones we've seen early in the semester, to give you a little bit of a sense of where things go from here. Strongly encourage you to start looking at some of these and trying these. Don't really need them for this course, but if you're seriously considering going further in STEM fields, it's nice to start trying some of these. The more you do, the easier it gets. You start to see, this is how I should approach this problem. Okay, any questions on the geometric series? So this is going to be our go-to sequencing series. The geometric series is exceptionally nice. It is unusual to have something that is so well behaved. So how many of you are econ or potential econ people? Okay, have you done the multiplier effect for money?
Yeah, we're just doing it right now.
Oh, excellent. So one of the best applications of the geometric series is if you give certain people money, how does that affect the economy? How does it ripple through? And it might be for every dollar you get, you might spend 80% of it. And then the people who get that money, they'll spend 80% of what you give them, and so on and so on and so on. And so this is to try to figure out what is the impact of a stimulus? How much will it do? Okay. I can't remember. Let's see. Have we talked about 3x plus 1 yet this semester? I don't think so. This is one of my favorite problems in mathematics. I do have a paper on this. There are two phenomenal quotes about this. One is Kakutani would travel around the country speaking about this problem, and people would go, oh, that's not so bad, and they'd spend a fruitless month working on it before giving up in frustration. And the other is from the great Paul Erdős, who said mathematics is not yet ready for this problem. It is deceptively simple to state. And here's my rule for my sequence. The n plus first term in my sequence is 3 times my previous plus 1, if an is odd, and it's an over 2 if an is even. Sometimes people instead do an plus 1 is 3an plus 1 if an is odd, and they do an over 2 to the k, where 2 to the k divides an, but 2 to the k plus 1 does not. And the notation we often use is double division of an to indicate that's the highest power that divides, no higher power divides. It's a good notation to have. What this is basically saying is, look, if it's divisible by 2, just pull out all the 2's in one step. Just save yourself some writing. So somebody want to give me a reasonable number that's not too large. There's one number that I really don't want, and I think I will just risk by not calling your attention to the fact and just gambling that no one says it. Yes?
4.
4. Okay, 4 is a really kind number. Thank you. So 4 is even. So I pull out. Do you want to pull out all the powers of 2 at once, or do you want to pull them out one at a time? First loud voice wins.
At once.
At once. So 4 goes to 1. 1 is odd, so what does 1 go to?
4.
4. So it will cycle forever. All right, I need another number. Another small, reasonable number.
7.
7. 7 is a great number. 7 is odd, so it goes to 21. Plus 1 is 22. 22 is even, so it goes to 11. 11 is odd, so it goes to 34. 34 is even, so it goes to 17. 17 is odd, so it goes to 52. 52 is even, so it goes to 26, but 26 is also even, so it goes all the way down to 13. 13 is odd, so it goes to 40. 40 is even, so it goes down to 5. 5 is odd, so 5 goes to
16.
16. 16 is even, 16 goes to 1. We now actually have a lot of data. What would you conjecture?
That it always ends with a cycle from 1 to 4.
It always ends with a cycle 1, 4. And in fact, all we have to do now is show that if we get any of these numbers, we know we cycle down to 1. So this is the conjecture. Always hit the 4-1 cycle. And then, of course, you stay in the 4-1 cycle. If you prove this, not only will you get an A+ for this class, I will get you a PhD in mathematics. I can call people up at Princeton. I can arrange it. You prove this. I'll even get you award money. Okay? I get several proofs of this a year from the Journal of Number Theory. A lot of people have tried to prove this elementarily without luck. It is incredibly hard. It turns out to be connected to a variety of interesting problems. It's a great example of a sequence. And this is a sequence that we believe is finite for any initial starting seed. No matter what starting seed you give me, it's believed that there will only be finitely many terms in the sequence. The result I proved with one of my colleagues is roughly, if you take a large starting seed and look at it as it iterates all the way down to 1, what can you say about the distribution of leading digits? So what's the leading digit of 40? 4. What's the leading digit of 2018? 2. So a lot of situations, leading digits are not equally distributed. You actually have a bias towards 1s of about 30%, and you only have about 4.5% 9s. So this is called Benford's law of digit bias. There's a lot of applications of this. The IRS uses this to look for fraudulent returns. Don't worry, individuals don't have enough data on their returns to be caught, but large corporations do. You can also use this for data integrity to make sure that your systems are transmitting the data without including errors. And so we were able to show that in some sense, the leading digits do have this bias. So there's a lot of interesting things you can do with sequences like this. I think I also give you the Lycherl sequence in the notes online. So the big questions we're going to have is, what is the limit of a sequence? Here, this is a situation where we can't even say what the limit is. Or we can say, but we can't prove. So the first thing is going to be, we have to reintroduce our concept of limits. So we saw limits when we were doing multivariable calculus, when we were talking about continuity. So we say the limit as n goes to infinity of an equals a is for any epsilon greater than 0, there exists an n such that for all n greater than or equal to n, the absolute value of an minus a is less than epsilon. So if you want to think about what this means, is here's a, you give me an epsilon, and then I choose the terms in my sequence. And maybe they're hopping around a1, a2, a3, a4, a5, a6. If the sequence converges to a, eventually from some point onward, we will always be within epsilon of a. Note, n could be a function of epsilon. Well, that makes sense. If I want to be within 1 over 100, that's not as severe of a restriction as being within 1 over googolplex. If I'm within 1 over googolplex, am I within 1 over 100? Yes. But just because I'm within 1 over 100 does not mean I'm within 1 over googolplex. So in order for the limit to exist, whatever tolerance you give me, so it's a game. You give me the tolerance, I tell you the n. And if you say, I actually want to be closer than 1 over googolplex, I want to be within 1 over googolplex factorial. This is beyond the ability of us to think of numbers this size. It's fine. I'll find another n that will work for that. Okay? So the first question is, what kind of properties do limits have? Could you have a sequence having 2 different limits? No. So our lemma, if a limit exists, it is unique. We've actually seen a proof of this before. Assume not. So if it's not, say here is a and here's a tilde. If the limits aren't the same, there's a separation between them. Choose epsilon less than, say, 1/4 of the distance between them. And so now, I know those epsilon intervals don't intersect. If I took epsilon to be, say, 3/4 the distance between them, then they could intersect in the middle. But by choosing epsilon sufficiently small, eventually I've got to be in here, and eventually I've got to be in here. I can't be in both because they're separated. So limits, if they exist, are unique. We don't always know that limits exist. So the 3x plus 1 is a great example of a sequence where we do not know if the limit exists. It's conjectured. The Lycherl one is another one. So who remembers the word that you associate to that sequence? So this is the palindrome problem. So somebody give me a number. Yes? 6. At least 2 digits. 16. So I take the number, if it's not a palindrome, so that means it reads the same backwards and forwards, I flip the order and I add. And now I get 77. And so it's a palindrome, so I stop. So the sequence goes 16, 77. And that's it. Right. Let's take a more interesting one. Let's take 29. If I flip the digits, I get 92. So I had 9 and 2 is 1. 9, 10, 12, 1. Oh, it's also a palindrome, and it came very quickly. So I would have now 29, 121. All right. Let's take, 6, 58. Now if I add, I get 8, 56. So it would be 14, 10, 11, right? 14, 15. This is not a palindrome. So I switch the order. 4, 1, 5, 1, 5, 6, 6, 5. So we get 658. The next one was 15, 14, and then 5, 6, 6, 5. Yes?
Will the end result always be, well, I guess not perfect, but like some sort of like Pascal triangle, or does it have anything to do with that at all?
Nothing with Pascal's triangle, unfortunately. So what might you conjecture looking at these first 3 data points?
The bigger the number gets, the longer it takes to bring it to palindrome.
Okay, so since you're saying the longer it takes, that seems to be implying that eventually it will become a palindrome. I'm trying to interpret what you're saying.
Yeah.
And that it could just take a little bit longer. I mean, I could give you a really nice number, 1,0,0,0,0,0,0,0,0,0,0,0,0,0,1, which would become a palindrome very quickly. But a generic number, it might take longer. So it's a fascinating conjecture. Will you always get a palindrome at some point? And I believe the answer is we believe not. And we believe most numbers will not hit palindromes. But I don't believe we have even one example of a number that goes on forever. And so what I'm doing here is I'm giving you some interesting sequences and series. You've seen the standard ones before. I want to try to give some that are a little bit more exotic. And the idea is, how do you attempt to model these? How do you attempt to understand these? And why do you care about these? A lot of these can be really good building grounds to understand dynamical systems. And for the 3x plus 1 problem, if you want, you could say roughly, if I choose a number at random, what's the probability that it's odd?
1/2.
1/2. What's the probability that it's even?
1/2.
1/2. What's the probability that it's even and divisible by 2 but not 4?
1/4.
What's the probability that it's even, divisible by 4 but not by 8?
1/8.
What's the probability that it's even, divisible by 8 but not 16?
1/16.
So you could actually model this as a process and then try to figure out what happens. So I have these 2 different operators, or maybe I have the odd operator and I have infinitely many even operators. And the ideas we've used to try to understand the 3x plus 1 problem are actually applied to understanding other dynamical systems. So our goal in the next few classes is to figure out how to handle these sequences and series. So a sequence is a collection of terms. The series is the sum. So can somebody tell me the difference between a necessary condition and a sufficient condition? So sometimes in theorems we talk about this is a necessary condition, sometimes we say this is a sufficient condition. If I tell you yes.
So for sufficient,
yes,
then we don't need any other condition.
we don't need anything else. It's sufficient for this to happen. Okay. What about necessary?
Like we need it, but it's not the only one that we need to prove.
Can somebody give me a necessary condition to pass a class with me?
Passing like all the tests.
If you pass all the tests, that would actually be a sufficient condition. Yes?
Maybe watching the videos?
Nope. Enrolling. You cannot pass a class with me if you don't take it. There are stories of students who have actually passed classes that they've dropped, and professors haven't noticed and have just been in the grade inflate mode and have passed everybody. And I know people who've gotten B's in classes that they did not take. But for me, you actually have to take the class to pass. It is a necessary condition. Is it a sufficient condition? No. Okay. There is a theorem I have, or conjecture. If you come to office hours, you pass. I have 2 decades of experience without any counterexamples to that. So a necessary condition is something that must be true. No, sorry. A necessary condition is something that must be true for you to have a chance of it happening. So here's a good question. Say you have a sequence AN, n goes from 1 to infinity, and you want Sn to be defined as the sum n goes from 1, let's do it this way. M goes from 1 to n of an. It's the sum of the first n terms. a1 plus a2 plus an. We want Sn to converge to some sum S. A necessary condition is what must be true about the ANs. So if I want the sum to converge, what must be true about the individual terms?
They need to get smaller.
They need to get smaller. Be more specific than getting smaller.
They need to be close to 0.
They need to be close to 0. They need to be converging to 0. The terms must be converging to 0. Imagine they weren't. If they're not converging to 0, then that means there must be some epsilon such that there are infinitely many terms in the sequence, at least epsilon from 0. And so if you were trying to converge, every now and then you would get boop, you get a little blip that pushes you a significant distance away. So this is a necessary condition. AN must be tending to 0 if we want to have convergence. If AN goes to 0, does that ensure that the series converges? Is it sufficient? No. So it's not sufficient. So we've seen an example of a series of terms that go to 0 that doesn't converge. Does anybody remember the series of terms that go to 0 but doesn't converge?
1 over n.
1 over n, excellent. 1 plus 1/2 plus 1/3 plus 1/4, 1/5, 1/6, 1/7, 1/8. And the way we proved this is we said, look, 1/3 plus 1/4 is greater than or equal to 1/2. 1/5 plus all the way up to 1/8 is also greater than or equal to 1/2. And if we just keep collecting terms like this, we see that the sum has to diverge. So whenever possible, you always want to try to do these special cases. Try to explore things and see what's going on. And here we see that it is not enough to have AN going to 0 for the series to converge. But if AN is not going to 0, then we're done. We don't have to worry about any further analysis. If AN is going to 0, then we have to roll up our sleeves, and then we have to really work, and we're going to try to develop some results as to when a series will converge. And some of these results are going to be technical. Big ones are the comparison test, ratio test, and root test. And then a little bit the integral test. Has anybody heard of any of these terms? Okay, this is where different people have different high school backgrounds. So for some people this will be review, for other people this will be new. Essentially everything we do lurking in the background is the geometric series. That is the nature of everything. The comparison test is essentially going to be, we compare this series to another series we know. If it's always smaller than a series that converges, it must converge. If it's always larger than a series that diverges, it must diverge. Diverge, go off to infinity. The difficulty with the comparison test is what do you compare it to? This is essentially where a little bit of the art comes in, is that you can have infinitely many things to compare it to. It's hard. The way you should view this is when you factor polynomials, when you factor quadratic, you can just stare at it and sometimes see the factorization. Or what could you do? If you don't see the factorization, what could you do to solve it?
Plug it into the quadratic.
Plug it into the quadratic formula. And that's the ratio test, the root test, where it tells you this is what you should be doing. And looking in the background, is the ratio and the root test know exactly what series to compare it to. They're comparing it to a very special geometric series. All the tests are really the comparison, but it's a question of how explicit must you be. All right, so we will continue with stuff like this and pick up the copy of the exam.